Okay, good day. This is Math 140 College Algebra. I'm Professor McCully, and this is the presentation for Lesson 7.3, Solving Simple Exponential and Logarithmic Equations. Let's get right to it. So today we are going to solve simple exponential and logarithmic equations. Let's keep a few things in mind. There's going to be a process here, and that process is going to make sure that you follow the rules of algebra and logarithms. When you're doing your logarithms, they are on the same level of the order of operations as exponents, and that makes perfect sense because exponents and logarithms are inverse operations of each other. And you also need not evaluate all the exponents if they are irrational. And just as a kind of a quick example here, um, e squared is a perfectly acceptable answer. All right. Please keep in mind the the definition of logarithm. That's going to help you quite a bit, especially if you know a and b and you're looking to solve for x, because you can go a to b and you just type that in your calculator. And then the property of logarithms that allows you to bring exponents down front is going to be useful, as well as log base a of a to the x equaling just x will also be useful to you. And so just as a quick review, if you have a logarithm that is the product of two values, you can separate that product into two different logarithms with a sum. If you have the quotient of an expression in a logarithm, you can separate that into logarithms separated by a subtraction. And then again, you can take, if you have a logarithm of an exponential, you can bring that exponent down in front. If you take the logarithm of both sides of the equation to apply property 3, the exponent must have no coefficient, and I'm going to show you an example of that in the examples here quickly. Almost all solutions involving logarithms are going to be irrational, and I've done a lot of examples where you could actually get a whole number or a terminating decimal as a solution, but in most cases in the real world, that's not going to be the case. And then number 3, while any known logarithm, and remember, when I say a known logarithm, I am talking about log or ln on your graphing calculator. Sometimes one choice is better and we make the problem easier. And the big one for that is when you see e in the equation, you definitely want to use ln as part of your solution because that's going to make it easier. Please make sure that you're checking all the answers, and remember that the domain of a logarithm is not all real numbers, it's just the positive values. So if you get a number that's going to make a logarithm, what goes into the logarithm negative, you're going to have to throw that out. And so we'll have an example of that also. So first, solve the exponential equation without a calculator, and we've done something like this before. Since it's without a calculator, these have to have the same base of some sort. So either 7 has to be changed into a similar base that you can change 49. Now we know that 49 is 7 squared. So just real quick note, 49 is equal to 7 squared. And we can also say that if we have a to the negative x, that's the same as 1 over a to the positive x. So I'm going to combine what I know there, and I'm going to say 7 to the x equal to 1 over 7 squared. Good job this morning. 7 to the x will be equal to 7 to the negative 2 using that second property. And then we can say x is equal to negative 2, put a box around it, and then done. All right, so solve the exponential equation. This will take a calculator, and I'm going to need to use the logarithm. And just as a recall from the notes, this is where I'm illustrating this first one. If you take the logarithm of both sides of the equation to apply property number 3, the exponential must have no coefficient. So right here, I have an exponential with a coefficient. So before I can do anything with this thing, I have to divide both sides by 5. That way I can get rid of that coefficient in front of that. And so that'll give me 8 to the x is equal to, well, if I go 5 divided into 320, 5 goes into 30 6 times with 0 left over, so I've got a 2, and then 5 goes into 20 4 times. And, here, and this one's going to come out to be equal because we can clearly see that 8 to the x is 64. 64 is a perfect power of 8. But let's use a calculator anyway. So we're going to say take the ln of both sides. And so we'll go ln 8 to the x equals ln 64. Now you could use log. I'm just using ln because it's shorter. And then I'm going to apply log base a of x to the n equal to n log base a of x. That's what I want. So I'm going to bring that x down. ln 8 equals ln 64. And then x will have equals the ln of 64 over the ln of 8. If I grab my graphing calculator, clear out what I had before, the ln of 64, close the parentheses, make sure you close the parentheses there, divided by the ln of 8 is going to give us 2, but we already knew that. So, all right, so solve the following logarithmic equation without a calculator in 2 ways. All right, so let's do case 1 here. Case 1. Let's go ln of x minus the ln of 2 equals to 0. And I'm going to say add ln 2 to both sides. And I'll have the ln of x equaling the ln of 2. And then I can say the property where you go log base a of x equals log base a of y if and only if x equals y. So we can just go x equals 2. That's a pretty easy way to do it. Case 2, let's say I'm going to go ln of x minus the ln of 2 equals to 0. And we'll use the property ln or log base a of x over y equals log base a of x minus log base a of y, and we're working this way. So since I have a subtraction, I'm going to condense them into a division. So I'm going to say this is the ln of x over 2 equals to 0. And then remember that ln is the same as log base e, right? So what I can do is I can use the definition of logarithm and say e to the 0 equals x over 2. And remember, anything to the 0 power that's not 0 is just 1. And then I'm going to multiply both sides by 2, and I get x equal to 2. And so in each case, we have x equal to 2. That's good. All right, next, simplify the following. And so I have ln e to the 2x minus 1, and I want you to recall that log base a of a to the x is just x, and since ln is just log base e, we can say that this thing is log base e of e to the 2x minus 1. And since I have log base a, log base e of e, this thing is just equal to the expression there, 2x minus 1. And that is our simplified version. So just another review of those logarithm properties. I've done it a couple times now. Log base a of a to the x is just x, just like ln of e to the x is going to be x, and log or a to the log base a of x is going to be x, and e to the ln x is just going to be x. All right, so they want us to solve the following exponential equation. So we want to figure out what t is, And so the first thing I have to do here is I'm trying to get t by itself, so I'm going to divide by 5,000. And so that'll give me 1 plus 0.005 all to the t power over 0.005. And so let's do that calculation. So 250, that's 250, and then I put 3 zeros to give me 1,000, divided by 5,000. It's going to give me 50. All right, so I've got 50 there, and so I'm going to multiply by 0.005. So we'll multiply that times 0.005. Oops, I think I have too many zeros. Yep, I got one too many zeros. So let's take out that 0. Let's take out that 0. Let's hit delete there. Hit enter. I get 0.25. So I've got 1 plus 0.005 to the t equaling to 0.25. And that should be a t right here, not a 2. All right. So now I take the ln of both sides, and that'll give me ln of 1 plus 0.005 to the t equals the ln of 0.25. I'll bring the t down, t ln of, and let's add that, 1.005 equals ln 0.25. We'll divide both sides by 0.005, so t equals the ln of 0.25 divided by the ln of 1.005. That I have to put in my calculator. ln 0.25 divided by ln 1.005, and I get negative 277.951. 277.951. T equals negative 277.951 approximately. All right, last one here. Solve the logarithmic equation. We have ln of 2x equal to 5. Here I'm going to use the definition of logarithm, and I'll go e to the 1.5 equals 2x, and then we'll divide by 2. X equals e to the 1.5, all divided by 2. Now you can leave it like this because it's going to be irrational anyway, or you can grab your calculator and you can go, because it's get a fraction and a decimal, e to the, let's say 1.5, close that, oops, I don't have a parenthesis there, let's delete, divided by 2 is 2.241. All right, well, that's all I got for today, folks. So the Marvel fun fact of the day: in Ant-Man 2015, during the 1989 flashback scene, de-aging effects were used on the 70-year-old Michael Douglas and the 57-year-old Martin Donovan to make them appear younger, and aging VFX were combined with a wig and makeup to the 33-year-old Haley Atwell to make her look a little bit older, so that these guys are of similar ages. Well, that's all I got for today, folks. Have a good one. Bye.